I'm good, Gemma. I'm doing good. Sorry, just was eating for a little bit. Apologies. Let me go on the main cam. There we go. Got it. Where did I put the other window? Oh yeah, there it is. Okay. Put this, Yeah, what you been up to, Gemma? Been pretty chill. Been working. Fair enough. That's all I've been doing was work, work, and more work. Haven't had too much time to myself the past few days. But I love having fun here on Twitch, so I can't really complain. Yeah. Now my feet hurt. Oh no. I've been in those. I've had those days before too. Back in the day. Back in the day, replay. Used to do a whole bunch of jobs. Was constantly on my feet all day. I remember those days. I've done too many jobs where especially working like when I was working in a theme park. Yeah, that was all day. You're on your feet. Yeah, exactly. Same with like if you're doing customer service, it's the same thing too. The theme park, I was on my feet all day because I had to be in like certain sections of the park, and then like customer service, you have to stand up all day, and you're just like, You're more thankful that break time comes around. You just want to sit and flop over. All right, just having some miso soup. Any plans for tonight, Gemma? That's literally what I'm doing. I'm a guest team service member. I don't. Oh no, jeez. How many hours do you work? I mean, you should be able to get a break if you're working like 8 hours. But again, okay, country work laws are different. Though I would suspect that they would be a little bit good. So over here we work a ton, so it may be a little bit more relaxed. You know what I'm saying? Oh, that's why. Okay. Well, that would explain that then. Yeah, if you're working like 4 hours a day, yeah, you're not gonna get like any breaks whatsoever. Wait, sorry about that. All right, here we go. Let's get started here. Ugh. Work 5 hours. Yeah, I think you have to work like 6 to 8 hours before you get like a 15-minute break. Even it puts you at that cutoff time. Maybe that's why you can't take a break. But let's be honest here. Remember, it's just for the in this case, it's just for the money. So you know what? Don't worry about it. You know, it'll pass. You'll be fine. No, you're working toward bigger and better things than being a guest service team member. So, You probably go to sleep soon because it's almost midnight? Yeah, sure. I know you're really tired today. That's not a problem at all. No, I understand if math puts you to sleep. It's totally understandable, Gemma. You're just like, oh, come onto my channel, Gemma, and you're like, oh my god, Professor Chibs is so boring. He talks about math. I'm like, oh, yeah, sorry about that. My bad. I'd be like, I kind of have to do mathematics. It's kind of like the job that I do, just by a little smidge, you know, just a smidge. What am I? Besides things I don't even know. There we go. Got that squared away. I'm not even gonna lie. Literally, I only come into your streams for a little chat and to catch up. That's not a problem. You know I'm here to catch up with you anytime. I'd be happy to, you know, a little chat and catch up is never a bad thing, right? I'm glad you just come to see little old me at the end of the day. You are a valued member. Absolutely. Definitely a good friend. I don't know, you treat me really well, so I can't really complain, you know. Let's see here. What a skipped. I forgot about that. Yep, 4 minutes to midnight. It's true. It's indeed 4 minutes to midnight. What time you got to work tomorrow? Or if you are working tomorrow? Or do you get to like sleep in a little bit? Do you get to sleep in a little bit? That's what I'll be doing a little bit. So I'll be sleeping in just a smidge. This will be the kind of the end of the week time here. So be a nice little relaxing night, just sitting and chilling, enjoying some good reading, maybe watching some videos. Nothing wrong with any of those. Ah, you're not working tomorrow. Oh, you got college tomorrow. Okay. What time you What time you got for college tomorrow? Is it a morning class that you have to do? Hey, Mizzou! Hey, buddy! Buddy! Holy smokes! Now there's a man I haven't seen in a long time. Holy moly! How have you been? 9:45 in the morning? Oh, you got plenty of time. You got like 9 hours to sleep. There you go. Mizzou, my man, how you been? Long time no hear. My friend. It has been a very long time since I last saw you. Or even heard from you. I hope you're doing absolutely fantastic, Mizzou. I hope things are going really well out there, by the way. Where are you at these days? Oh, you have to leave by 7:50. Oof. 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 Welcome welcome to my class stream. Yeah, we'll be starting in about a couple minutes or so. You came at the right time. I heard that you got my I heard that I saw that you follow my channel there. I heard you got the lowdown from like Ant, I think. So Ant or Prez, I think. Oh, nothing. Maybe it was Prez, but yeah, man, I've been teaching on Twitch here for a little over a year since the pandemic started. Yeah, just you gotta take like the public transportation there, Gemma. That's why it's probably like 750 because it takes about 2 hours to get there. Ooh, that's a little rough. Surprised there isn't a train that goes right by there. I think there would be a train. Mizzou, you gotta tell me what you've been up to, buddy. I actually really want to know. In all honesty. Where are we? Oh yeah, right there. All right, let's do this here. Alrighty, good stuff here. We got a few more people coming into the chat. Very good, very good. All right, I like what I'm seeing here. We got a lot of the regulars. It's good. It's good. All right, we're ready to get rolling here. Yeah, we even get special guests. Look at that. I'm telling you, can't go wrong in the chat when you got really good people like Gemma and Mizzou coming in. Man, Mizzou, man, you're always welcome anytime, Mizzou. Anytime, my friend. All right. All right, let's go ahead and get going here. We'll do some intros. Start it. You ready to learn? Excelente. I'm glad you're ready to learn, man. I know I couldn't teach you much over Star Wars because, I wasn't that great, but maybe I'll teach you a bit about math here. Okay, let's get started today. Welcome back to Thursday, end of the week time today. So today, ladies and gentlemen, today we are going to finish off talking about limits here. So last time we talked about how to find limits, algebraically, how to do it through factoring, how to do it, through graphing. We took a look at how limits kind of work there. So today we need to go ahead and look at one more type of limit, actually in section 2.4, and then we'll get into section 2.5. See if we can get a little bit into section 2.6. Just depends how long it's going to take us to do section 2.5. So, but definitely we'll go ahead and do section 2. Go ahead and take a look here at the big board. Take a look at that. Bam. All right. All right, so checking out the big board here, let's take a look at numbers 10 and 11 here, respectively, on the handout. All right, so let's look at what are some properties of infinite limits. So the last type of limit here that we are going to encounter in this section anyway is an infinite limit. Meaning to say we take the limit as x approaches infinity or minus infinity and then see what value that we get. So again, if it gets larger and larger, are we approaching a particular value, or are we approaching maybe other values? Or are we just approaching infinity? That's entirely plausible. In any case, here we have two particular properties associated with infinite limits. With infinite limits, for example, a generic property is, say, 1 over x to the n. So if I took like 1 over infinity, like a ridiculously large number, 1 divided by that particularly ridiculous large number is so infinitesimally small that it pretty much is 0 at the end of the day. So it would be approaching 0 there at the end of the day, the larger and larger that number got. And the same thing applies here for minus infinity, okay? You get smaller and smaller, and yeah, you're going to get an infinitesimally pretty small negative number, and so that is to approaching 0. So hence, while you have these two rules here, No problemo. All right. What we want to do here with these two particular rules is to go ahead and um, figure out exactly how we can evaluate certain functions if it goes toward infinity. All right. So again, there's a couple ways to express infinity. Again, you could do the same techniques we talked about here last time. We could look at the graph. We could look at a table. All right. We could look at both of those things and what happens at positive infinity and negative infinity. That's all well and good. But let's look at a few more practical ideas about how we can evaluate infinite limits. So I put the key here in this case, and we're going to come back to this key here in just a moment. But let's take a look here at, first and foremost, let's look at number 73. All right, so we're going to look at number 73 here. All right, and let's go ahead and do this up together. Ba-da-ba-ba. Number 7. Okie dokes. So here we're going to take the limit as x approaches infinity of 3x plus 2 over x minus 5. All right, seems fair. Okay, so what do we want to do here in this case in order to find this particular limit? All right, let's go back to the key here for this guy. What we want to do is to divide each term by the largest degree term and apply the property of infinite limits, which are these two guys here, and see what's left over. So exactly what does that mean here? Again, limits can be positive infinity, negative infinity, that's possible. Okay, now let's identify first here. All right, so let me ask this question here. So among these four terms that you see here, the two terms on the top and the two terms on the bottom, we need to identify the largest degree term here. Okay, so what is the largest degree term according to this particular uh, function here? What's the largest degree term that we can run with here? Okay, so the largest degree term would be 1, right? Okay, so the degree would be 1, right? I agree with that. So Chip's correct, Liwen is correct. Okay, so meaning to say remember we have x to the first here. Okay. Oh, that's adorable. Send me a picture later, Gemma. Um, all right. So we have x to the first here. So what we're going to do here is we're going to divide the key here in this case. Let me go ahead and point out what the key here is to divide everything. We're going to divide everything by x to the first, or just x. Okay, or I'll put an x to the first here on purpose just to highlight the degree. Now every term is going to be divided by. So what does that look like here? We're going to have 3x divided by x plus 2x divided 2 over x. Sorry, 2x divided by x. We'll have x divided by x and minus 5 divided by x. And we're going to take the limit as x approaches infinity in this case. Okay. Got on a picture. All right, cool. So let's take a good look at what happens here when we divide everything by x, which is the highest degree term here in between all of these function guys. So first of all here, we see the x's cancel here. We have 3x over x. These x's cancel. That leaves you with 3. 2 over x we can't do much with right now, so we'll come back to that in just a second. X over x, of course, those cancel, but those leave you with 1. So we get 1 minus 5 over x. I say, okay, seems fair. No problem. All right. Now, we want to take the limit here. So can anybody tell me what's the limit as x approaches infinity of 2 over x? What's the limit? So 3 we can leave alone. But what's the limit as x approaches infinity of 2 over x? What's that going to be? So if I plopped in infinity in here, right, really super large number, say 0, right? Okay. Okay. Good. All right. And probably saying, well, why is that 0? Well, remember, let's go back to our properties here of infinite limits. Even though this says 1, okay, you could put any number up there. You could put 2, 3, 4, 5. It doesn't matter. Okay, that number over infinity is going to be so small, it's practically 0. So this is where we're going to use that property here that we talked about here in number 10. Is effectively this cancels out because the limit as x approaches infinity of 2 over x is 0. We have 3 again plus, and we'll put that in black here, 0 over 1 minus and then a 0. And so here we get 3 over 1, which is just 3. So the limit here, without having to do too much work and just using the property there, all right, we did it. Good stuff. Okay. Any questions about that example so far? We'll do another one, of course, but questions? Hopefully that wasn't too bad. We need to take a look at another for sure, so. Again, if you have a question, go ahead and type that out in chat. If you don't have a question, type no in chat, and I'll move forward. Okay. Good stuff. Where did the fractions go again? Well, the fractions actually changed over to 0 here, Nick. What would be considered a large enough number where division by infinity isn't 0? There is not a number large enough. Either the cancellation happens, in which case x is never considered, okay, or it's always going to go to 0 there, Elizabeth. So anything divided by infinity will, it's not yeah, it'll go, the limit will be equal to 0. That's correct. So then, so to answer your question there, Elizabeth, and to answer Nick's question there as well, what happened here is that if we took each individual limit, okay, if we took the limit of 2 over x, that's going to be equal to 0. The same thing applies for 5 over x. If you did the same thing there, Nick, you would get also 0 here for the limit. So, thanks, Gemma. I'll take a look at it a little later. So that's where we went ahead and got both of these turned to 0 because we're using that property there. All right. So by using the property there, that's why we can claim that both of these limits will be 0 by default. Are there any other questions? Please let me know if you want me to. We're gonna do another example here, so hopefully that'll highlight it a little bit more. But any other questions before I move forward? Hopefully everybody's got that down. Okay. Alrighty. Okay. Alrighty. Next, let's try another one. Let's try. Hey, good night, Gemma. You have a great one. Wow, Milky. I don't know what to say. That's how does that even work? I don't even know how that even works. Hope you're doing well, Milky. Let's do number 76 here. To the limit as x approaches infinity. A lot of pain is all you gotta know. I'm sure. I'm sure. I believe you wholeheartedly, 100%. Oops, should be squared there. How are things out in Kent, Milky? I hope the weather's very nice over there. All right. Okay. So the limit as x approaches infinity of 2x squared plus 3x plus 1 divided by x to the fourth minus x squared. Again, we're going to take the same exact approach here. We're going to first find the term that has the highest degree. All right, that's what we want to do. So what term has the highest degree? What term has the highest degree according to this particular problem? At least talk about that here first. What term has the highest degree according to what we see for this problem? What do you guys think? Okay, so Lee Wen says 4. Is that correct? For our or going to be our degree here that we want to look at. Let's see if they got that one special. That's fine. Okay, so in this case here, we're going to divide everything by x to the fourth. All right, that's what we're going to do here. So let's go ahead and divide everything by x to the fourth. That's what we're going to end up doing. So we'll divide 2x squared by x to the fourth plus 3x over x to the fourth. Everything gets the same treatment. Okay, now let's take a good look here at what happens when we divide by x to the fourth. So in this instance here, we get 2x squared over x to the fourth. So we get 2 over x squared. All right, so not much we can do about that. It is what it is. Same with the next one here. We have 3 over x to the third, since 1x cancels out. And then we have 1 over x to the fourth. Fine. Okay, next we have x to the fourth over x to the fourth. That's going to be 1. And then we have 1 over x squared as well for this part. Right? All right, so here's the question here. Let's talk about the main question. The main question here is, what's the limit? All right, so we need to now take the limit as x approaches infinity of everything in here. What's the limit as x approaches infinity of all these guys up top? The limit as x approaches infinity of 2 over x squared, 3 over x to the third, 1 over x to the fourth. What's the limit for all of those guys when they approach infinity? What's that going to be? Going to be here. Okay. Right? Just like we talked about before here, right? No matter what, in this case, we have some random number over infinity squared or whatever. Well, infinity squared just makes it smaller at the end of the day because you're dividing by a larger number. So in fact, in this case here, That's going to be 0. Second guy, also 0. Third guy, also 0. Okay, in all three cases here, that's going to be 0. And the same thing can be said here for the bottom. That last term is going to just drop out and be 0. So putting this together here, we're going to get a pretty simple answer here. So we have a numerator here of 0, denominator of 1, so 0 divided by 1 is 0. And so there we go. We have our final answer. And that's how we can go ahead and find the derivatives here. Not derivatives, sorry. The limits here. Try to think ahead. The limits here at x is equal to infinity and negative infinity. All right. Questions about infinite limits before we move forward. Hopefully not too bad. Any questions? Alrighty, let's move forward then. Okay, next. Here's my handout stuff. Okay. All right, let's take a look at sections 2.5 and 2.6. Okay, we'll see if we can get into a little bit of 2.6 here today. No promises on that, just depends on how fast we go here. But let's talk about the first thing here, which is something that we talked about here yesterday. We talked about here yesterday is when we first introduced limits. We actually talked about, again, finding a limit on one side or the other side. And those guys separately are called one-sided limits. So let's, again, if I take a look at the notation here now, maybe it's a little bit tough to see on the screen. So let's make it a bit bigger. All right, so take a look at the notation here. Here we have the limit as x approaches a from the negative side of f of x, and limit as x approaches a from the positive side of f of x. Okay. Now, what do each of these mean here, respectively? If we want to come from the negative side, essentially what that means is that you're approaching it from the you're approaching A here from the left. You're coming from the left. You're going left to right. Okay, so it's like I'm driving down this road from west to east. Okay, that's essentially what you're doing here from the negative side. For the positive side, it's just the opposite here. Again, you're approaching A here from right to left or going from east to west. All right, so essentially, that's the easiest way to kind of view them. Is like, okay, coming from the left, going left to right. All right, coming from right to left if you're coming from the positive direction. And again, I guess I will say this about one-side limits. Okay, they may or may not exist. Okay, they are a little bit more loose than the definition that we had here last time for limits. Reason why is because that one-side limits can exist and they can be different. Okay, but that difference, doesn't have, that difference there only matters when we talk about an overall limit. Here we're just talking about two sides, two separate sides, really. Okay, so let's take a look at some examples here of left and right limits here. So let's take a gander. Okay, and this is on page, what page is this? Get 130, there we go. Alrighty. Take a look at this guy right here. All right. We're going to try and find some one-sided limits. We'll see exactly how it goes. We'll take a look at some pictures. And yeah, no problem. Okay. let's take a good look here at number 2. Okay, let's look at number 2. And number 2 is a good example about where this is going to work. Okay, so uh, how we visualize these one-sided limit guys. So maybe by words it's a little confusing. I'd be like, yeah, that's kind of fair. It can be certainly confusing if you're not sure what to look for. I said, okay, well, let's just look at it from a picture perspective. That'll make things a bit easier. So let's say, for example, here, we take the limit as x approaches a from the negative side of this particular function. What would the answer be here? Again, a being 3, so change that up here. What would the answer be here in this case? If we're approaching 3 of the, whatever this function is, what is that one-sided limit going to be? What's that value? That value going to be the limit as x approaches 3 from the left. So again, imagine if you were going left to right on this graph. What value what value at 3 would you end up with? Hmm. Hmm. All right. Well, I'll wait for a little bit until somebody can give me an answer. I don't want to answer myself because it's like, okay, I know this. Hopefully. Hey, Athena, how's it going? Say the answer here is hello. How's it going this afternoon / evening, Athena? So Lee Wen says 3. Chip says 3. Okay. So let's take a look here. If we're coming on the graph here, coming from left to right, we're coming on this road, if you want to call it a road here. We're coming from west to east. So coming from the west, we're going to go all the way up this road here, and we reach the destination, which is going to be, in this case, 3. Eating Portillo's, I was thinking about getting that, and then I went to Sushi Burrito. So, I didn't. Let's take a look at the limit as x approaches 3 from the positive side of this function. Yeah, I think I overate a little bit. I had a poke bowl, and then I had a burrito. So coming from the positive side, we get 5. That is correct. Very good, Elizabeth. That's right. So coming from east to west, we're driving on this road right here, and that goes all the way up to 5. Okay? Remember, we're heading toward that destination. That destination here would be 5 in this instance. All right, let's take a look at another here. One more. All right, how about number 5? Number 5 is the limit as x approaches 1. Say from the negative side here. What's that going to be here? Limit it as x approaches 1 here. The answer is 0. Good, Elizabeth, that's right. So again, coming from left to right. So left to right, going right here, we end up at y is equal to 0. So that's correct. You just stopping by, you're more than welcome anytime, Athena. 100%. You know we love you. We love you. All right. Let's do the other one here. What's the limit as one approaches from the right-hand side of the function here? The answer is indeed 2. Good. Right. So if we come from east to west, again, right to left, then there we go. Bada bing, bada boom. 2 is your winner. I hope that's starting to make a little bit more sense now, okay? I know we've seen a couple of pictures here. But we're starting to make a little bit more sense about how we're working with one-sided limits here. You see, it is a little different, but it's not as bad as it may seem. Yeah, it makes sense. Okay, good. I know it sounded like from when you guys, since you guys weren't responding, I thought, oh, is it getting a little confusing? I was like, ah, man, that kind of stinks. So, want to be sure that everybody's like, oh, okay, I get it. So I'm like, all right, that's fair. All right, let's take a look at some other ones here. Okay, so the next one here is going to be find the indicated one-sided limits. All right, so let's take a look at this here and see what we get. Okay, so it says the limit as these are pretty simple. So I'll find one that's actually a little bit tougher. Okay, yeah, we'll do that one. All right, so let's go ahead and do number 25. Okay, so let's look at 25 here. Just show that one off here. 25 says the limit as x approaches 0 from the positive side of 1 over x. Over here. So 0 from the positive side of 1 over x. So the real question is, what exactly is the answer to this problem? What's the trick to this or key? So the key here is to go ahead and use the graph here once again. So you can use points here, and that's nice. But why don't you use the graph on the calculator, and that'll be significantly easier. So let's go ahead and look at this on the calculator. See what we ah, okay. Hello. There we go. Okay. So in the y equals menu here, we're gonna go ahead and hit 1 divided by x. Okay, so that's what we want here. Now we're going to go ahead and take a look at the graph here. Again, around 0 coming from the right-hand side. So the important part here is the direction. Let's take a look at the graph key here. Okay, so judging from this graph here, all right, what would be the limit here as x approaches 0? What would be the limit here in this instance? So we will have the graph here. Want to look at 0 coming from the positive side, the right side there. We're working from right to left. What value does that graph approach from that side? Is it approaching 5? Let's take a look. Oh, shrink that down here for a second. Oh, wait. That no wonder I took that away. Is it approaching 5? Are you sure about that? It's a good guess, though. 5 is a little bit outside this, is a little too small here. 0, right? Doesn't it approach y equals, does it approach y equals 0? Actually, let's answer that question. Does it approach 0 here? As a y value, as a y value. So we're not talking an x value here, because that's what we're trying to figure out. It's not really touching 7. So don't take it at base value based on, just these tick marks here. All right, it's not do not exist. In this case here, one-sided limits normally do exist. Most of them do. So wouldn't it be just infinity, says Emma. The answer is that is correct, Emma. It would be just infinity here. This, okay, I'll show you here. Let's take a look at the table for this particular function, around 0, but again, bigger than 0 since we're coming from left to right, from right to left, pardon me. But take a look at the table here. Table, please, not calc. Okay. As this x, let's say this x gets smaller, around 0, we can even pick values closer to 0. So let's pick a really small value. Okay. I'll just start putting in random numbers here. You don't have to do what I'm doing right now, but so I'll put in random numbers around 0 here. Again, they'll be bigger than 0. Let's put 0.1. That's a number around 0, so that's fair. By 0.001. Okay, getting bigger. Point up is point lots of ones. Okay, 0.2356. Okay. So you can see here that the numbers, the smaller they get, the larger they're going to get, going towards infinity. So infinity here is going to be our answer for this problem. So one of the things that you'll have to be very careful about is, again, noting that it doesn't go up to that tick mark here. It's actually, you need to look at the numbers around it, again, specifically in that particular direction, again, more than 0 in this case, and then you'll be able to find your answer. So does not exist doesn't occur too often here for these guys because they're one-sided limits and not two-sided limits. Okay, any questions about that? Any questions? Any questions? No? And you guys gotta just let me know if you have questions, okay? Ask me anytime. Ask me anytime. All right. Okay. And then there's several others that are pretty easy. Look at, I don't know if I want to do that one necessarily. Okay, we'll go ahead and skip those. Okay, pretty easy. All right, next, let's take a look at the next part here. Next. Kind of weird. Trying to open this up. But okay. That's that there. Okay. Alrighty. Close this down here. All right. There we go. Got it. All right. Okay, so after talking about one-side limits again, Let's reiterate what we discussed here last time. It says, what is true about one-sided limits and limits in general? If both one-sided limits are the same, then the limit exists and it equals that value. Okay, so a little cutoff there, but it equals that value. So if both one-sided limits exist and they're both equal to the same number, just like we talked about last time, you're coming from both directions here, you're both hitting the same city, all right, when you're driving, then that's exactly what the limit is going to be at the end of the day. Okay, so we did discuss about that last time here, and that's still applicable here as well. So if you're doing it from a pictorial representation, make sure that from both sides of the equation, they're both coming to the same number there. And in that case, you can say, oh, okay, yeah, that's the limit. Okay, let's take a good look here at the next concept. So the next concept here is going to be number 3. What is a continuous function? All right, so let's take a look at the base definition here of a continuous function, and I'll work our way up. So a continuous function is a function that's continuous at a number a if f of a is undefined, is defined, excuse me. The limit exists, and the f of x is equal to f of a if you just plug and chug the number in, and you magically get something back out. So that is what this part here is reflecting. Let's go ahead and take a look here, though, at some other guys. All right, and we're going to see how continuity works. So again, one thing I reiterated here, and probably something to definitely write down, so is kind of this part here, as it does help a little bit here into dealing with continuous functions. So it says if a function doesn't have a hole in the graph, okay, that's another no-no for a continuous. At that point, and a continuous function would have a graph, it would result in a graph in which you draw without having to lift up your pen or pencil. So you draw a graph and you never lift up your pen or pencil, you connect the dots perfectly. That is considered a continuous function of some variety. All right, now if we take a look here at some examples. Oh, let me I out of that like that. Second, folks. Oh, there it is. Okay. All right. Okie dokes. So we're just going to go ahead and find out what values are going to be continuous or discontinuous, whatever the case may be. We're just going to run with this here. So let's take a look at these exercises here. We're going to start off with something simple, work our way up, right? I promise you it won't be too hard. It won't take up too much of your time. So a lot of good visualization is very helpful for these questions as well. Okay. So for each exercise, determine the values x, if any, at which the function is discontinuous. At each number where f is discontinuous, state the condition for continuity are violated. Okay, so let's take a look here. Is 39 continuous or discontinuous? 39, this function we see here, they give us the definition. Is that is that is that a is that continuous or not continuous? It's dis. I don't know what dis means, but so 39 is continuous, you say? So why do you feel that this is continuous? for 39. That's fair. Hey, you spelled it right. you you got it. You got it spot on there. Not continuous. Why do you think it's not continuous, Li Wen? Why do you feel that this is not continuous? Oh, because it's a line? But what's unusual about the graph for number 39 here? What's unusual about that particular graph that you see on the screen? Disregard that. And where are we discontinuous then, Elizabeth? So where does it break off here? Where would we have to pick up our pencil in this case? What value for x? All right. Now I do gotta clear something up here. So at what value is the function discontinuous? X values only. Okay, so not your y values, your x value. X is equal to 0. Okay, good. That is correct. Okay, so I know that seems strange again, but it will ask you to put it in terms of the x value there. I'll put dis down here, just like said here, to shorten it. Phrase, okay? And we're shortening, we're discontinuous at x is equal to 0. That's correct. How about, let's take a look. Most of these questions are pretty straightforward, but let's see here. Okay, what about number 42? Number 42, is that continuous or discontinuous? All right, Elizabeth says continuous. Anyone else? Chip says continuous, okay. Anyone else? We get continuous or discontinuous? What do you guys think? Okay. Continuous, okay, E-Man says. I feel there was something about these lines when I took calculus in high school. They're continuous, but I don't remember exactly. Yes, there is a property associated with 42. Li Wen says continuous. Okay, so that's correct. This is continuous everywhere. That's true. All right. So it's dis. I see how it is today. I see how it is. Get a little bored, throw down the diss track, legitimate diss track. See what I did there? All right. Very good. Very good. Totally did it. Oh, that's pretty bad. The jokes are going to get terrible. All right. Okay. Now, sometimes we don't have sometimes we're not going to have the graph here. Let's take a look at other questions here with continuity. Okay, so let's take a look here at number 50. It says find the values of x in which the function is discontinuous. So it's like, okay, you miss a few payments or whatever, and you know, they start, this, you want to see what would shut it down, which payment would shut it down. So what value would shut this function down? In this case, the function being x plus 1 over x minus 1. What value would make this bad and make sure that we do not have continuity? So essentially, we're doing the same thing as we did for like the domain questions, finding out, what values say don't work, and then excluding them and keeping everything else. So what would make this discontinuous? Are there any values for x we can plug in where we're not going to get an answer back? -1. Okay, let's take a look at this a little bit more carefully here. Be sure it's -1. If I want to find a value that makes this bad, maybe -1 isn't the best value to choose. Okay, 2? Well, maybe not 2. All right, Lee Wen says x minus 1 is equal to 0. That's correct. That's part of the answer. So the thing is, in this case here, we have a rational function, right? So we want to be sure, we want to see, okay, what values for x is going to make the denominator equal to 0? Because again, we're not allowed to divide by 0 here, okay? So let's add 1 to both sides here. So here we're going to have x is equal to 1. Okay, so the only answer here that makes this discontinuous is if x is equal to +1. Again, because we would have a 0 on a denominator and we wouldn't be able to find an actual defined answer. So we know for a fact we are discontinuous there. If there are other factors, we would factor it out and then see what we get here. In this case, this is all we got. Okay, very good, very good. Let's try another here. That's so in this case here, this would x equal 1 is where we're discontinuous. I know it asks, it says for what values would this make it continuous? Again, you would exclude 1 here. I'll guess I'll show that off as well. I guess that's not the worst idea. It's not the terriblest idea that I just thought of. Okay. Okay. All right, so if we want to write this out here, x would not equal 1. A way to write this out here is from -infinity to 1, and then union 1 to infinity. If we can write it out in interval notation, this is what the domain, or again, in this case, the values that would say make it continuous, excluding 1 here because 1 doesn't work. All right. Any questions about that? Any questions at all? Let's do one more. This time I'll have you guys give it a go. Then we'll take a break after this. Which one I want? Sure, let's do that one. So how about this one here? This will be 52. All right, so here we got x minus 1 divided by x squared plus 2x minus 3. Okay, can anybody tell me here what value or values make this discontinuous? And then think about what that answer would be in interval notation. So let's take a good couple of minutes here. Let's have you guys give this a try. Again, I'll give you a hint. You'll have to factor the denominator here. So think about that, and we'll give it a try. Okay? Let's give it a go. I'll give you a couple minutes of which to do this. I'll be put on mic here, so mute here, so. You're actually super close, Lee Wen. You're actually super close. Would you have to flip them? So it'd be -3 and 1? Okay. Okay. Good, good. All right, so if you factor the bottom there, you would get x plus 3, right? And x minus 1. All right? So you get x plus 3 and x minus 1. So what you did there is you set those both equal to 0. And the signs have to be flipped. Okay, so x would be minus 3, and then x would be 1 here as a result. So these two numbers are what makes it discontinuous. Can anybody tell me what the domain of this function is going to be? What's the domain of this function? You got it? Okay, good. What's the domain of this function here? Because we want to exclude both of these guys. We want to find out where it's continuous, right? What's the domain? And we can easily express this as x can't be minus 3, and it certainly can't be 1. We want to exclude those. How can we write that as an interval? What do you guys think? How can I write an interval notation? Are you guys familiar with interval notation? You guys okay with it? You guys decent with interval notation? You guys gotta let me know. So I know things have been a little quiet here today, so I need you guys to kind of give me the skinny. That's really close, Chip. You're actually off by just one. Actually, you're off by one thing here. I'm actually going to flip that. It's that first one you see there. So instead of minus 3 comma infinity, flip them around and make the infinity a negative, because you're going to start from minus infinity, go up to minus 3, right? Minus 3 to 1 is correct. And then 3 to 1 to infinity. Good. That's correct. Can we do a quick review of interval notation? It's been a while? Sure. So really quick here, let me bring up a handout here from my previous class and talk all about this. Yeah, here we go. Okay. So to talk about interval notation here. All right, so yeah, that's correct. That's correct, Contessa. That's correct. Very good, very good. All right, so with interval notation, we have parentheses and we have brackets. Okay, so at least let's talk about this here really quick. So we have parentheses and we have brackets. So if we have parentheses, that indicates not included. We don't want to include those values in our interval notation. If we have brackets, that means it is included. Okay, again, with less than or equal to or bigger than or equal to for being included. Strictly less than, strictly bigger than will be people or things or numbers we want to exclude. Okay, now there are rules here for this, and many of you have gotten this good so far. But the rules go is that, again, you have to start with the low number and you have to go comma the high number. So it always goes low comma high here. Hey FD, how you doing? It's going really good today. How you been? Hopefully you're doing good, my friend. All right, anytime we have positive and negative infinity, we're going to put a parenthesis next to it, okay? Because positive and negative infinity don't technically exist. So we actually have a very, again, it's pretty straightforward. Again, negative positive infinity will always have a parenthesis next to it. Easy peasy. And if we have solid circles and open circles on a graph or something like that, or anything of some variety, a solid circle would mean a bracket, okay? A open circle will mean a parenthesis. Okay, so again, just going back to our problem here, using our problem here with our domain. Our domain is negative infinity. Again, that's the low number, comma the high number here, which is -3. We go -3 to 1, and then 1 to infinity. Are there any questions about that? I hope that makes. I hope that shakes up a little bit of the cobwebs there, Elizabeth. No, no questions, Emma. Okay. All right. Good stuff. Okay. Okay. Let's go ahead and take a short break here. It is 7:05 right now. We'll come back at. We'll take a. We'll take 10 minutes here. We'll take 10 minutes. That's fine. We'll take 10 minutes. Let you guys decompress because we've been at it for over an hour here. Let's decompress here. Let's get back to, things have been a little bit slower, so that's fine. So let's go ahead and take a short 10-minute break. We'll be back at a quarter after, 7:15. All right, and we'll keep going forward. Oh, that. Go to the big screen here. There we go. Woo! Go ahead and take a look what I have to talk about. Property. Okay. Wonder if he's still there. Maybe he stepped away for a little. Check that. That's a great question. Where is that thing? Long time. Bam. Why does it take so long to do? Okay. That's fine. Alright. Is that right? Okay. Okay. Let's see if it- Okay, let's get back to work here really quickly. Just to clarify something for you here. I was just checking a couple of things here. Uh, Pratchip, are you still there? Just want to be sure that you're still there. Get started here with the second half of class here. Just wondering if Pratchip, you still there? I hope you are. I'll come back to. Once he comes back, I guess I'll talk about that question he asked. He asked me a particular question. I want to acknowledge that question. I'll wait for him to come back and then we'll talk about it. All right. In any case, let's go ahead and continue moving forward here with continuous functions. Okay. So let's take a look here at question 4. Question 4 talks about properties of continuous functions. So let's go ahead and discuss that here. So there's a couple major properties here. First and foremost, number 1 here, f of x is equal to c, where c is constant, or f of x is equal to x, which is just like a simple line that kind of goes up. That's going to be continuous everywhere. So no matter what, if we have a constant number, which is just kind of like a flat horizontal line, or just a regular line kind of going up here, those are going to be continuous everywhere. It doesn't matter. You're going to be just fine. You don't have to worry about those too much. Um, Also, where you're continuous here is basically if you add two functions together, subtract two functions, multiply two functions, divide two functions, provided that the denominator is not 0, then you're going to be continuous everywhere. You're going to guarantee that you could be continuous everywhere for that for those guys. So it's going to be continuous at x is equal to a for those particular guys at those values. Um, okay, you're back. Okay. What I wanted to talk about here really quickly. You asked me a question via email regarding the homework stuff, right? So I just want to be sure that I kind of want to acknowledge that here on the today. So I just want to be sure that you asked you weren't sure about how it worked. Yeah, okay. So I was looking at the assignment that you asked specifically about. So I'm just looking at it right now. Okay, and I see what, how you did for the individual questions. The one thing that I don't see here um is I just don't see like 1, 2, 3, 4, 5. So 5 of the problems here are haven't been you didn't put responses to. So 5 of the problems you didn't put responses to. So what it did was, since since you didn't respond to 5 of the problems, all right, those points of the problems weren't added in. All right, so technically you have 23 out of 31 points for that particular assignment, which is why it's showing you the percentage for that assignment that it is. So if you go back, you could easily go back. It doesn't matter. You go back and fill in those 5 problems that you didn't do. Then you'll get those points, and then it'll change from the current grade that you got uh, to full points there. So that's what you need to do, is just submit those questions that you didn't answer. So even if you skip questions, it'll still count those as like, hey, I didn't do it. So that would be like a 0 points on that particular question. So I hope that that answers the question about how it does the grading there. So that's a homework based question, but I think everybody should know. Again, just so there's no surprises or anything like that. Yeah, yeah. So just go back. You could go back and stuff like that, and you could go back and just again do those 5 questions that you skipped. You'll get that 100% on that particular assignment. You have a question about the final. Do we take it in our own time like we do the homework, or do we take it during the class period? Yeah, so basically the way I'm going to set up the final here, Elizabeth, is I'm going to go ahead and have it done on your own time. So yeah, I don't want it done during class period. That's kind of crazy. So I know for people who take summer courses, you may have 2 or 3 courses going on, which is quite a handful, and maybe you're doing work on the side. No, I think it would be better for everybody if we went ahead and kind of do it on your own time. Of course, the only thing that you'll have to wait for is when I go ahead and make it up and release it to you. Then we'll go ahead and talk about, of course, the rules behind it and all that jazz. But that is no, purely done on your own time, and will be cumulative for the course. So like I said, I want to make this a stress-free experience. So I don't want to be like you have to do it on this day at this time. Like that doesn't make any sense to me. That's just ridiculous. So like I said, I'm not in the business of making it hard for you guys, okay? I'm in the business of making it, hopefully making it where you can do the best that you can without having to feel like ridiculously overwhelmed in a subject that's already hard enough. So that's not that. Trust me, I'm not. Like I said before in the first day, I'm not here to be your enemy. Okay, I am not here to be your enemy. We're not adversaries, to start. Okay, I'm on the same level as you guys, and I totally understand where you're coming from. So yeah, I'm not gonna play like, yeah, evil games with you guys. Trust me on that. That's why that's why the first day I'm like, here's all the homework. It's all available to you, you know. Because if I did that, it's like, okay, yeah. First, like yeah, here's all the homework available to you. It's like, okay, you could get started and work at your own pace. It makes absolute, like, it's ridiculous. Like, oh yeah, you gotta get this done. Boom, 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 boom. I get that there's deadlines there and stuff like that. But you guys are human beings. You're not robots, okay? Sometimes it's going to take you a little bit more time to do something because we're human. Okay, so I mean, heck, I did the same thing too. I hated being under like supreme amount of stress. It was really hard. It really is. Sometimes it just made it so much where you're just like, uh, you know, if you ever get that feeling like in the middle of the semester, I don't know if this has happened to you, right? You ever get that feeling in the middle of the semester, that one class, right? And that one class, whatever that one class is, it drags you down in all your other classes, and you get super stressed out about this one class, that basically for every other class that you have around that class that semester, you just totally shut down and you don't want to do a darn thing. And then you don't get really good grades because of it, obviously, but you just shut down. You're just like, this is way too much. It's like you just feel like you feel like complete ass, and you're just like, screw everything. I'm gonna go over here and I need some space and I need to go do things that, like, to decompress or de-stress or whatever. You know, because I've been in that situation too. If you have, then I trust me, I've been in that situation. I absolutely there was a class that I had a long time ago which definitely fell into that category. Yeah, it hits you really hard, right? It hits you really hard. Now, summer classes are even harder in some respects because we have to cram everything into 8 weeks, right? So everything is like super compressed and super rushed. Trust me, I would want to do this much slower if I possibly could. And trust me, we're going to finish on time. That's not going to be a problem. but everything is super compressed and can be already overwhelming as it is. But again, that's why I have the notes, so that way take it at a nice little pace here, you know. But you know, I would say, you know, we've all had those classes before, and I don't want to be that class. I don't want to be that class where we're just like, wow, this is like super super difficult. Stress eating is my best friend. Stress eating is always my best friend too. I ain't gonna lie, bro. Chip. He's dreading this course, but the way you approach it makes it. Yeah, see, doesn't because I understand where you're coming from. Having almost failed out of college for that same exact reason. Yes, I know where you're coming from. Okay, I've been there. I've been at the very bottom of the barrel. Okay, I've gotten bad GPAs. I've all failed classes before. Okay, I've done the whole 9 yards. It's not fun. You feel really bad because you felt you wasted time and money, and you're like, you felt that the teacher wasted your time and money. You feel like you're wasting your time and money, and all you got out of it was a large headache and lost time. So especially the lost time really helps. Really is the kicker. So because it's like, oh, that's one more semester I have to make up now. Now that's 4 more months out of my life that I have to go do another course in order to get what I want. And that's like, then you start beating yourself up, and it's just like a vicious cycle afterwards. So I totally get where you're coming from on that. It is not easy to get over that hump sometimes, but this is not the course where that's going to happen. Okay, this is not the course where I am going to make damn well sure that this is not the course where that's going to happen, okay? I guarantee that if you want to make it hard on yourself, okay, but I don't want you to make it hard on yourself either, okay? Trust me, I don't. I really legitimately don't. Okay? The first hour of this class may be incredibly boring talking about continuous functions and stuff. We're all slipping into food comas and stuff, but hey, okay? It wasn't super overwhelming. It's just like plodding along piece by piece. So, yeah, that's kind of like where I'm at. Full transparency, 100%. Okay. Having said that, you're like, holy cow. All right. Stress eating project. Got that right. Get those late night runs to Taco Bell, man. Uh, all right. Let's take a look. Let's go back. Let's go back to this question here. Let's go back to this question. We got a little bit more to do here today. All right. So number 4, what are the properties of a continuous function? All right. So the first property of continuous function is if we have a constant function, or if we have a f of x is equal to x, again y is equal to x, that's going to be continuous everywhere. If we add two functions together, subtract two functions, multiply two functions, divide two functions, that's going to be continuous at a, again for division, just provided that the denominator is not equal to 0. That's going to be continuous at x is equal to a. Okay, so again, if those values exist, you're going to go ahead and make the assumption here that you are continuous at those particular values. All right, so you can go ahead. Again, those are two particular properties about continuity. Now, let's talk about this next part here. This is the last part here for this section, and then section 2.6 will be right after that. All right, but we'll talk about number 5 here. What is the intermediate value theorem? So the intermediate value theorem is the last thing we talk about regarding continuous functions. Let's go ahead and read this off here together. Oh, it would be helpful if I could show you the handout, right? You guys got to tell me, show me the handout because I'm an idiot. I know. I couldn't see the handout. Fair enough. Okay, let me scroll up here. Scrolling up to the handout. Voila, magic. Here it is. Okay. All right. let's look at number 5 here. Let's read off the intermediate value theorem, number 5. If f is a continuous function on a closed interval, a comma b, and m is any number between f of a and f of b, then there's at least one number c in the interval ab such that f of c is equal to m. Okay, now you're probably saying, whoa, timeout. Let's take a large timeout. What the heck? What's all these letters? What does it mean? Why is it here? Why is life so difficult with all these letters? Okay, in reality, this isn't as bad as it may seem. Um, I would just take a, if you read it carefully, it's not the worst thing ever. But if you draw a picture with these letters in mind or with something simple, right? If you draw it with something simple here, it actually turns out that it's actually rather straightforward. Okay. So how does it work? Let's try it with something really easy, okay? So something really easy is like looking at 0, okay? So let's look at 0 here. Now, if you had let's say you had a continuous function, and let's say this is the particular curve here. Let's say this is the curve for the function, whatever. Okay, and let's say this is the x-axis here. So this is the x-axis. Okay, so let's say, for example, here we had two numbers. We call it a, and let's say we call this number over here. This is let me put a here. All right. This is a here, and let's say this is b right here. Okay. So A and B are right here, somewhere along the curve. All right, so that means that this point here is going to be f of A. All right, and this point here is going to be f of B. Now, based on this, how I drew this generic curve, okay, this general curve. I don't care what this function is per se. It's a continuous function, though. That part is for sure. Again, it's a pretty smooth curve. It has no breaks. It has no holes in the graph. Okay, nothing of that sort is really going on here. What this is basically saying, this intermediate value theorem says, is like there is a number in between, such that there is a number in between a and b where it's going to equal that number. So let's say f of a here, we'll call this 3. Okay, we'll call this 3. All right. Let's say the y value there is 3. I'm just making it up here, so don't worry about I'm just making up the y values here. And let's say f of b, whatever that is, that's going to be -7. Okay, so we have one value here, we plug it in for a, and somehow it's magically -3. The other value for b, we plug it into the function, that's -7. Those are where those two values are. Now, why is this so important here? Well, because let's say I'm looking for 0, right? Let's say this is 0. This is where this 0 value is right along the x-axis. So essentially we have a and b. Between a and b, we have some random interval between a and b, whatever x values a and b are. And basically my contention is that 0 is in between 3 and -7. Okay? So 0 is a number between 3 and -7, right? So everybody would agree 0 is a number between 3 and -7. And so the contention that this basic theorem is saying is like saying, okay, there's some random number between a and b, whatever they are, so that this guy here is that f of c. So c here is between a and b, and so there's somehow, some way, because it's continuous, f of c here is equal to 0. Some random number that's between a and b, we'll call it c, is going to end up to be 0 at the end of the day, just like this picture is kind of saying. Okay. Are there any questions about that so far? Does that make sense to everybody about how, the reasoning behind this? Because again, a lot of letters going on here, but again, when you just plug in numbers, it's pretty simple to see here. You find out, what number is between those two y values. Maybe there's a number in that interval that's going to be between. Again, that's because it's continuous. So, are there any questions about that before we move forward? Well, we're going to look at an example here, of course, with like more numbers, but want to be sure that everybody kind of understands the basic idea behind this. Okay, remember, feel free to ask me questions if you're confused, but we're going to go ahead and take a look here at an example, which I think will clear up a lot of the other things here. So let me check to see. Okay, that's the one I'm doing. Okay. All right, so let's go ahead and go back to the book here. And we're going to go to that one there. So okay. So we're going to take a look here at number 84. Okay, so let's look at 84. So 84 talks about the oxygen content of a pond, okay? So the oxygen content T days after organic waste has been dumped into a pond is given by, and as you can see there, that function, okay, pretty large function, but whatever. All right, percent of its normal level. Show that f of 0 is equal to 100 and f of 10 is equal to 75. Okay, well, those two guys are pretty straightforward. Let's go ahead and do them out here really quick. Really shouldn't take us too much time here, at least. We just need to plug and chug these particular numbers here. So we have f of t equals 100. Put in the function here. Divided by t squared plus 20t plus 100. All right, so if you plug in 0 into this function, it's actually fairly simple. I'm just going to kind of paraphrase it. You can use a calculator if you want to. It won't change a thing. So you'll actually get 100. These hundreds will cancel out. You'll actually just end up with 100. And then f of, what do they have? F of 10. Okay, what is f of 10 here? The 100 on the outside here. We get 100, 200, 300. We get 300 up top here. That means we get 400 down here. And so here we get 75. So, all right. So this is pretty simple to see. Just plug and chug the numbers here, no problem. So if you can imagine here, this is what we have here. Okay, so we have an interval here. Our interval here is between 0 and 10. Okay, and we have f of 0, which is 100, and f of 10, which is 75. Okay, so f of 0 is 100, and f of 10 is 75. So this will be important for part B here. So part B here says, use the intermediate value theorem to conclude that the oxygen content of the pond must have been at a level of 80% at some time. Okay, so use the, gotta go ahead and see if where it is equivalent to, if it's 80% of the time, using this theorem that we just talked about. So the real question is 80 between 100 and 75? Let's answer that question first. Is 80 between 100 and 75? Is that true? Yes or no? Last time I checked, it was. All right. Yes. So the answer is definitely yes. 80 is definitely between 100 and 75. So what you can make a conclusion is that since 80 is definitely between 175, then what we can make a conclusion about is that somewhere between 0 and 10, so somewhere between 0 and 10, all right, so some random number, f of that number is going to equal 80, okay? And that number has to be between 0 and 10 because it's a continuous function. Okay, so we have to take it to the bank that that's going to have to occur. All right. Are there questions about that? Okay. Now we don't know what that number is. Okay, we need to go ahead and solve for this, of course. But we can at least make an easy conclusion here. We don't have to guess. We don't have to guess like too many numbers here because we know what at least it's between here at the end of the day based on this intermediate value theorem. Okay, so let's go to letter C. Letter C says, at what time or times is the oxygen content at 80? Okay, all right, so at what times is the oxygen content at 80? Now, there are several ways to attack this particular problem. All right, so we're going to go ahead and use the calculator for this one here. And let's go ahead and see how we can met this out. Okay, so using the calculator here, we're going to go to the y equals menu. We're going to enter in the function that we see up here. So this is going to require a little bit of finagling. So pretty big function. Was it x squared? Now on the calculator, this is what it'll look like. I know this looks a little messy. I had to put a double parentheses though because I have two quantities here in this particular instance. I'm going to go ahead and hit the graph key. Let's go ahead and take a look at what this curve looks like here, if we can see it. Guess not from that point of view. We'll go to zoom fit. Hopefully we'll get a nice curve. Okay, so pretty big. All right, this isn't going to tell us too much, unfortunately. I'm going to need to at least finagle it a little bit more. Let's take a good look here at, let's see if I can finagle it this way. I want to see if we can go ahead and do that. Not what I wanted. Oh, wait. Let me see if that works. Oh, okay. Oh, there was one way I did this using the table. This way wasn't right. Doing both is ask. Maybe that was the way. Unless I have to do it more. No, alright. So it wasn't that way. How did I do this again? I did this a while ago. Oh yeah, that's right. I remember how I did this again. Alright. Okay. Okay, so the way I went ahead and did this is, if I recall correctly, is I went to second and trace. And I made another line here. Actually, I remember that. I made another line here at 80. And I want to figure out where these two lines intersected. So I kind of cheated a little bit. I said, okay, if I have the expectation that I should get 80 as my final answer here, and if I put it on a graph, I'm going to have two lines here. One is the red line, one is the blue line here. I just go ahead and go to second and kind of what you talked about here last time. You say kind of go to second and calc, and we go to intersect. We kind of talked about it a little bit last time with the demand and supply equations that we did here previously on the calculator. So we just pick the first curve, we don't care. The second curve, again, don't care. Just hit enter. Guess, again, just hit enter again. And there we go. We have our intersection here, which is right on the very bottom here. So here we can see that x here is equal to 3.82. Okay, so 3.82 is going to be where we get our answer. Now we know this is our answer for certain because 3.82 is in between 0 and 10. Because that's the expectation, right? The expectation is that we're going to have, we want y is equal to 80. Well, where does that happen? Okay, well, it happens at 3.82 here in this particular instance. And that will confirm our answer. Are there any questions about that? I don't know why I forgot that method. But yeah, that's a lot easier than doing that's a rough method if you do it that way. So makes life easier if you do it that way. I want to use a quadratic formula. Oh my god. No, that's terrible. All right, and so that is going to be the end of section 2.5. Okay. Okay, very good, everybody. All right, so for next time here, we're out of time, but for next time here, what we're going to be doing is sections 2.6 and 2.7. We're actually going to be starting the real meat and potatoes here, which is really starting to get into talking about derivatives. So derivatives here is going to be the primary focus here of everything we're going to be doing starting next week. All right, and I'm going to have a little bit more details for you regarding exams and whatnot. So I'm going to be working hard this weekend to kind of get exams and stuff kind of set up. And then what we're going to do is next week we're going to go ahead and talk about a lot of the details regarding the exams. All right, so I will have more to tell you here next week, and certainly how the exams will be conducted, and that includes we'll talk about that, and then hopefully that will be satisfactory to get these 3 tests out of the way as well. All right. All right. Well, I want to, again, let me go ahead and switch to the let me go switch to the cam here. All right, again, I want to thank everybody here for coming out here to the stream once again. I really appreciate it very much. You guys have been super patient with me. Thank you so much. You guys are amazing. Coming out here at 6 o'clock to 8 o'clock here every single day, wanting to learn a little bit of mathematics. With me. So all of you, I really appreciate the effort and time you guys put in to want to watch a scrub like me. So I want to again thank you very much, everybody. I love you all. All of you are absolutely wonderful people. All right. Everybody also have a great weekend. Okay, again, we are going to be back here on Monday, same time, same place, 6 o'clock here, right here on Twitch. All right, I really appreciate all of you here. Thank you very much. Thank you so much. Again, if you have any questions, you guys know where to contact me. contact me on Discord or the email there. I'll be more than happy to answer any and all of your questions. All right. In the meantime, though, everybody stay safe, stay healthy, but most importantly, stay sane. Have yourself a very wonderful weekend, everybody, and we will see you again next week on Monday. All right. Take care of yourselves. Have a great one. All right. And I'll be here for you if you need me. All right. We will see you all later. All right. Take care, everybody. Bye.